Welcome back, students, to another part of our lesson, work energy power, and today we will be introducing the topic collisions. In common language, a collision is said to occur when objects crash into each other. For example, collision between automobiles, a hammer striking a nail, collision between billiard balls, carom coins. Collisions range from the microscopic scale of subatomic particles to astronomical scale of colliding stars and colliding galaxies. Often, the collisions are too brief to be visible, though they involve significant distortion of the colliding bodies. In general, we define a collision as an isolated event in which two or more colliding bodies exert relatively strong forces on each other for a relatively short time. Thus, actual physical contact between two bodies is not necessary for a collision. For example, an alpha particle speeding towards nucleus of an atom gets deflected by the electrostatic force of repulsion. The alpha particle is said to have undergone collision with the nucleus. The major object of the study of collisions is to find out as much as possible about the forces that act during a collision from the knowledge of the state of particles before and after the collision. In fact, all our understanding of the subatomic world, electrons, protons, neutrons, muons, quarks, comes from experiments involving collisions. Two key rules of the collision game are: number one, law of conservation of linear momentum, and second, law of conservation of energy. Types of collisions. Collision between particles have been divided broadly into two types: elastic collisions and inelastic collisions. Elastic collision. A collision in which there is absolutely no loss of kinetic energy is called an elastic collision. For example, collision between atomic and subatomic particles are elastic collisions. Practically, collision between two ivory balls can be taken as an elastic collision. The basic characteristics of an elastic collision are: the linear momentum is conserved, total energy of the system is conserved, the kinetic energy is conserved. Obviously, the mechanical energy, that is kinetic energy, is not converted into any other form of energy like heat energy, sound energy, etc. The forces involved during elastic collisions must be conservative forces. Inelastic collision. A collision in which there occurs some loss of kinetic energy is called an inelastic collision. As there is always some loss of kinetic energy in most of the collisions, therefore collisions we coming across in daily life are generally inelastic. If two bodies stick to each other after colliding, the collision is said to be perfectly inelastic. For example, mud thrown on a wall sticks to the wall. The loss of kinetic energy of mud is complete. The collision is perfectly inelastic. Similarly, when an arrow gets stuck in a target and the two move together, the collision is perfectly inelastic. Likewise, if a meteorite collides head on with Earth, it becomes buried in Earth. The collision is perfectly inelastic. You can get some more information regarding elastic collisions by observing this picture, and we have already discussed that during an elastic collision momentum is conserved, kinetic energy is also conserved. Talking about inelastic collision, the basic characteristics of inelastic collisions are that the linear momentum is conserved but total energy is conserving. Kinetic energy is not conserved. A part of mechanical energy is converted into some other form of energy, which might be in the form of heat or sound. Some or all the forces involved in an inelastic collision may be non-conservative in nature. For example, when we drop a super ball onto a hard floor and the collision between the ball and the floor is elastic, the ball would lose no kinetic energy because of the collision and would rebound to its original height. However, the actual rebound height is somewhat shorter, showing some loss of kinetic energy in the collision. Therefore, the collision is somewhat inelastic. However, if we neglect the small loss of kinetic energy, we may approximate the collision as elastic. When we drop a golf ball on the ground, it rebounds to nearly 60% of its original height. Therefore, this collision cannot be approximated as elastic. It is an inelastic collision. Again, when we drop a ball of wet putty onto the floor, it sticks to the floor and does not rebound at all. As the putty sticks, the collision is a perfectly inelastic collision. We normally think of elastic as referring to something that always returns to or keeps its original shape. Thus, in an elastic collision, objects maintain their original shape and are not deformed by the action of forces. On the other hand, objects in an inelastic collision are deformed during the collision and lose some kinetic energy in the form of heat energy, sound energy, internal elastic potential energy, and so on. It should be clearly understood that total energy and linear momentum both are conserved in elastic as well as inelastic collisions. However, kinetic energy is not conserved in an inelastic collision. Coefficient of restitution or coefficient of resilience. In actual practice, collisions between all real objects are neither perfectly elastic nor they are perfectly inelastic. They are called imperfect or semi-elastic collisions. The degree of elasticity of a collision is determined by a quantity called coefficient of restitution or coefficient of resilience of the collision. It is defined as the ratio of relative velocity of separation after collision to the relative velocity of approach before collision. It is represented by E. It is given by velocity of separation, that is the relative velocity of separation after collision, divided by relative velocity of approach, that is before collision. So we may write down E to be equal to V2 minus V1 divided by U1 minus U2. Where u1 and u2 are velocities of the two bodies before collision and v1 and v2 are their respective velocities after collision, as it is quite clear in the picture. For a perfectly elastic collision, relative velocity of separation after collision is equal to relative velocity of approach before collision. So in that case, E is equal to 1. For a perfectly inelastic collision, relative velocity of separation after collision is equal to 0. Therefore, E is equal to 0. For all other collision, E lies between 0 and 1, as you can see in the picture. So we shall discuss about collisions in systems that are closed, that is no mass enters or leaves the system. Further, the systems are isolated, that is no net external forces act on the bodies within the system. In fact, external forces, that is gravity and friction, are negligibly small compared to the strong impulsive forces during collision, which are internal forces. So we shall discuss about elastic collision in one dimension. It involves two bodies moving initially along the same straight line, striking against each other without loss of kinetic energy and continuing to move along the same straight line after collision. Suppose two balls A and B of masses m1 and m2 are moving initially along the same straight line with velocities u1 and u2 respectively. Now, when u1 is greater than u2, then relative velocity of approach before collision is equal to relative velocity of approach before collision is equal to u1 minus u2. Hence, the two balls collide, as you can see in the second figure. Let the collision be perfectly elastic. After collision, suppose v1 is the velocity of A and v2 is velocity of B along the same straight line, as you can see in figure C. When v2 is greater than v1, the bodies separate after collision and relative velocity of separation after collision is equal to v2 minus v1. Let's mark these two equations as equation 1 and 2. Linear momentum of the two balls before collision is equal to m1 u1 for the first ball plus m2 u2 for the second ball. Similarly, linear momentum of the two balls after collision should be equal to m1 v1 plus m2 v2. Now, since it is an elastic collision, so as linear momentum is conserved, so we can write down total final momentum to be equal to total initial momentum. From this we can get, taking out m2 as common, we get v2 minus u2 equal to, taking out m1 as common, u1 minus v1. Let's mark it as equation number 3. Total kinetic energy before collision is also equal to total kinetic energy after collision, since again the collision is elastic. So we can write down half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. Now, by arranging the terms and taking out half as common throughout and cancelling it, we get m2 v2 square minus u2 square equal to m1 u1 square minus v1 square. Let us mark it as equation 4. So we have equation number 3 and equation number 4. Dividing 4 by 3, we get m2 v2 square minus u2 square divided by m2 v2 minus u2 to be equal to m1 u1 square minus v1 square by m1 u1 minus v1. So first of all, you can cancel out m2 and m1, and then if you check the numerator, you find that it is in the form of the algebraic identity a square minus b square. So a square minus b square is equal to a plus b into a minus b. So we can write down v2 plus u2 into v2 minus u2, and in the denominator you have v2 minus u2. This is equal to, similarly on this side we can write down v1 plus u1 and u1 minus v1 divided by u1 minus v1. So now we can again cancel these terms, and thus we are left with v2 plus u2 is equal to u1 plus v1, or v2 minus v1 is equal to u1 minus u2. So hence, in one-dimensional elastic collision, we may write that relative velocity of separation after collision is equal to relative velocity of approach before collision. So now from equation number 5 we may write down v2 minus v1 by u1 minus u2 is equal to 1, and by definition this is equal to e. So therefore coefficient of restitution for perfectly elastic collision is equal to 1. Now let us find out the formula for final velocities after collision, that is v1 and v2. For this we will be using equation number 5. From equation number 5 we can write down v2 to be equal to u1 minus u2 plus v1. See, v2 will be equal to u1 minus u2 plus v1. We will substitute the value of v2 in equation number 1. In equation number equation number 3. So on substituting, we get m1 v1 plus m2 u1 minus u2 plus v1 equal to m1 u1 plus m2 u2. m1 v1 plus m2 v2, in place of v2 we have written down this expression, is equal to m1 u1 plus m2 u2. Let us solve it out. So we will get m1 v1 plus m2 u1 minus m2 u2 plus m2 v1 to be equal to m1 u1 plus m2 u2. So now if we take out v1 as common, you get m1 plus m2 to be equal to m1 minus m2 times u1 plus 2 m2 u2. This step can be obtained by rearranging the terms. Therefore, we get v1 to be equal to m1 minus m2 divided by m1 plus m2 times u1 plus 2 m2 u2 by m1 plus m2. Similarly, for finding out v2, we can see that v2 is equal to u1 minus u2 plus v1. So as v2 is equal to u1 minus u2 plus v1, therefore v2 will be equal to u1 minus u2, and now we will substitute the value for v1. So it will be m1 minus m2 by m1 plus m2 times u1 plus 2 m2 u2 by m1 plus m2. So now we need to solve it out. We get u1 taken as common 1 plus m1 minus m2 by m1 plus m2 plus u2 2m2 by m1 plus m2 minus 1. So on solving, you get v2 equal to 2 m1 u1 by m1 plus m2 plus m2 minus m1 by m1 plus m2 times u2. So this is the expression for final velocity v2. We had obtained already the expression for v1. So these are the expressions for final velocities. Now let us discuss some special cases. Number 1, when m1 is equal to m2, when both the masses are equal, and let us assume it to be equal to m, then v1 will be equal to 2m u2 by 2m, so that will be equal to u2, and v2 will be equal to 2m u1 by 2m, and that will be equal to u1. So when two bodies of equal masses undergo elastic collision in one dimension, their velocities are just interchanged. Now this result has an important application in a nuclear reactor. Fast moving neutrons in a nuclear reactor are slowed down by making them collide against the nuclei of a moderator. As nuclei of hydrogen atoms or protons have roughly the same mass as that of a neutron, on collision, fast moving neutrons are slowed down, transferring their energy to protons. Therefore, hydrogenic materials like heavy water or paraffin are best suited as moderators in nuclear reactors. Coming to the second case, when target body is at rest, that is u2 is equal to 0, then we get v1 to be equal to m1 minus m2 divided by m1 plus m2 times u1, and v2 is equal to 2m1 u1 by m1 plus m2. Now we may discuss three sub cases, like for instance, now if m1 is equal to m2, then what shall we get? If m1 is equal to m2, v1 will be equal to 0 and v2 will be equal to 2m1 u1 by 2m1, that is equal to u1. That is, body A comes to rest and body B starts moving with the initial velocity of A. Obviously, in such a collision, 100% kinetic energy of A is transferred to body B. Second, if m2 is much greater than m1, that is, the target body is very heavy, in that case we will put m1 to be equal to 0 because it is negligible. So we will get v1 to be equal to, from this expression, v1 to be equal to minus of m2 by m2 times u1, and that will be equal to minus of u1, and obviously v2 will be equal to, putting m1 0, v2 will be equal to 0. Hence, when a light body collides against a heavy body at rest, the light body rebounds with its own velocity and the heavy body continues to be at rest. This is what happens when a ball rebounds to the same height from which it was thrown on striking a floor. The third one, when the target is lighter than the moving body. In this case, we put m2 to be equal to 0. So we get v1 to be equal to m1 by m1 times u1, that is equal to u1, and v2 to be equal to 2 m1 u1 by m1, so that is equal to twice of u1. Hence, when a heavy body undergoes an elastic collision with a light body at rest, the heavy body keeps on moving with the same velocity of its own, and the light body that was initially at rest, the target, starts moving with double the initial velocity of the heavy body. So these were the discussions regarding elastic collision in one dimension. Now we will be having one more session on collisions, in which we will be discussing about inelastic collision in one dimension, and elastic collision and inelastic collision in two dimensions. That shall be discussed in detail in the next session. Thank you.